This clip will go over two calculation of friction problem. This is the first one, so if you haven't solved it yet, please hit pause and take a few seconds or minutes to solve it. Let's start with part A. So a 50 Newton crate is at rest on a horizontal surface. The coefficient of static and kinetic friction between the floor and the crate are respectively 0.4 and 0.2. If no horizontal force is applied to the box, how large is the friction force acting on the crate? So essentially what I'm asking you is that we have a force, an applied force initially that was there or that could be there, and we remove that force. So that what is the friction in this situation when there's no other force that are acting? Well, we know that the sum of force on the x-axis has to be 0. And since there's no other force acting than possibly static friction, it forces us to see that the static friction will be 0 in this case. Makes sense. We don't have any force that are acting trying to displace the block, so friction does not have to do anything. So in this case, the static friction will simply be equal to 0. In part B, if a horizontal force of 6 Newton pointing to the right is applied on the box, what is the friction force acting on the block? So in this case, this force, the applied force, is equal to 6 Newton. So we want to know what will be the size of the friction force if this is to stay in equilibrium, because we are expecting that it will stay at rest. Can we make that claim? It's not necessarily obvious. So the first thing that we should check is what is the maximum static friction. To find the maximum static friction, we just do μs times the normal. So in here, this will be 0.4 times the 50 Newton, which is the normal of the crate. So we get a value of 20 Newton. So you see that in here, Fs max is indeed greater than this. So since 6 Newton is smaller than Fs max, we know that it will stay at rest. So now let's look at part B and C, which we'll actually do at the same time. So in part B, if a horizontal force of 6 Newton pointing to the right is applied on the box, what is the friction force acting on the block? So we want to see what's going on, but in order to figure this out, we also need to know whether the block will be moving or not. So C is asking what minimum horizontal applied force is required to put the crate in motion. So let's start by looking at these two together. First thing to do, not very surprising, draw a circle around your object so that you're sure that you're not missing any of the force. What are the force acting in here? We will have the normal force. We have Fg that is pointing down. And we also have a friction force that we expect to be pointing this way. And very likely static, although we have not checked that condition yet. Once you get this, you can write your two equations for the sum of force. You can do this even before you start thinking or reading the questions. Sum of force in x will give us that we'll have the force applied, which is the 6 Newton, minus the force of friction is equal to 0 if we assume that it's at rest. And then we will have for the sum of force on the y-axis, which is equal to 0, we'll get that the normal minus Fg is equal to 0. So you see that from this equation we can get that the normal is indeed equal to Fg, so it will be equal to 50 Newton. This equals 0 in here is something that we should check. And in order to check it, we want to see what are the conditions in order for the block to move or to stay at rest. So the condition is that the F applied, if it is smaller than Fs max, then we know that the block will stay at rest. So in order to see this, we need to calculate what is the Fs max in here. And this Fs max will just be 0.40 times the normal. Okay, so coefficient of static friction times the normal. Normal is just 50 newtons. So this will give us 20 newtons. So this means that in order for the object to move, what is the minimum force required? We need an F applied that will be greater or equal, actually it should be strictly greater I guess, than 20 Newton, which corresponds to the maximum static friction. Okay, and now that we have this, we know that in case B, so if we go back to case B, I'll change color to make it a little bit better. So in B, we know that the force applied is indeed smaller than 20 Newton. So this means that it will stay at rest. And from the equation on the sum of force and X, we therefore see that Fs will be equal to the force applied. So it will compensate to keep it at rest, and it will be equal to 6 Newton. Alright, so that's basically to solve this question. Next question is a little bit more interesting. It's roughly at the test level question. So we have a 10 kilogram block pushed with a force of 40 Newton, acting at an angle of 36.9 degrees above the horizontal, but the block stays at rest. I want you to calculate the normal force and the friction force. So hit pause, take a few minutes, and come back when you're ready. So to solve the problem, not very surprisingly, the first thing to do is to identify the forces that are acting and then to draw the free body diagram. So start, as usual, by drawing a circle around your object and identify all the contacts. So we have contact with the ground, we have contact with this applied force, and that's it. So when we draw our forces, we will have the normal force that is pointing straight up, as usual, perpendicular to the surface. We'll have static friction because the force is pointing slightly, the applied force is pointing slightly to the right. I'm expecting to see static friction pointing left. And we, of course, have the applied the force due to gravity, the long-range force, so we'll also have Fg in here. So once the forces are all identified, we're ready to draw the axes. It's terrible. Let me start again. Okay, much better. So we have the x and the y-axes, and we can just redraw our vectors. So we'll have the force applied that is pointing in here at an angle of 36.9 degrees above the horizontal. It's important to keep track of the angle as we go. Then we have the normal force straight up. We have the force of friction pointing to the left. And finally, the force due to gravity that is pointing straight down. Okay, you can see that the force applied can be decomposed. It's the only one that is not on one of the axes already. So we'll have the applied force on the x-axis. And we also have a component that will be the applied force on the y-axis. Let me just move these a little so that we have more room to write the equation for the sum of forces. So that's the next step. That's really where we want to get at. So we know that the block stays at rest, so sum of the force on the x-axis will be equal to 0. And then we go back to the free body diagram to figure out what's on the x. Well, we have F applied x that is pointing to the right, so positive direction in here. And we have minus the force of static friction, because static friction is pointing to the left. Same thing for the y-axis, so we will have sum of force on the y-axis is equal to 0 as well. And on the y-axis, we have a value in here of positive for the y component of the applied force and the normal. So we will have F applied y plus the normal minus Fg will be equal to 0. So really, what we want to do next is restart from these values in here, understanding that the F applied x will just be equal to 40 Newton times the cosine of 36.9. We know that we need to use the cosine because it's the side that is adjacent to the angle. And we can do the same thing for the y-axis, or the y component of the force, which will be equal to 40 Newton times the sine of 36.9 degrees. So combining all that information, we will be able to get the answer very quickly. Allow me to make a bit of room. I'll just put the y components on one side, x on the other side. So we have that piece of information here, that piece of information there, and we're ready to finalize this. So Fs in here, we know will simply be equal to the x component of the applied force. So we can plug the values in here. Cosine of 36.9, that's about 0.8. So times 40 newtons will give us about 32 newtons. So we have our answer to part B, actually. And to answer the value of the normal, we just want to solve this equation. Be careful, the normal in here is not equal to Fg, because the force applied is pushing the block up a little bit. So the normal will be reduced. The ground does not have to apply as large a force. So using this equation, we can see that the normal is equal to, I bring Fg on the other side. I do the same thing for the force applied, so it will become negative. We have Fg minus F applied y. Fg, I need to remember what's the mass of the block. It was 10 kilogram times the acceleration due to gravity, 9.80 meters per second square, minus 40 newtons sine of 36.9 degrees. This part in here, sine 36.9 is 0.6, so times 40, we know that this will be minus 24 newton. And then on the other side, we have 98 newtons. So when we finalize this, we get that the normal force will be equal to 74 newton. And that's it for this problem.